Hello, I'm Mike Platt, Technical Services Engineer for Coracoat Limited. This is one of a series of technical videos we're producing to inform our customers and colleagues about various technical aspects of protective coatings. This video is on the subject of cold wall testing. Cold wall testing is related to moisture vapor transmission rate and insulation value. It's one of the tests indicating the performance of a protective coating, but is important as the test simulates real life. All organic materials are moisture vapor permeable, and almost all organic coatings will be subject to moisture in service. In vapor form, it will to some extent or another proceed into and through the coating. This bottle has collapsed due to vapor loss through the plastic. Vapor transmission causes coating defects such as blistering and corrosion of the substrate under the coating, so it's important to limit the amount and velocity of vapor transmission. The velocity is increased at temperature by the opening of the coating matrix and condensation effect at a cold substrate. It is only possible to reduce it, not stop it. The basis of what we do at Coracoat is to reduce vapor transmission and velocity in coatings to such a small amount by using impermeable flake barriers that effectively no corrosion takes place at the substrate. If moisture vapor gets down to the substrate and it is cold, there will be a condensing effect that causes vapor to form liquid in microvoids. Once formed, any small temperature movements in either the process or atmospheric conditions will cause that liquid to expand or contract. When it expands, it will push the coating away from the substrate, and then if it contracts again, it will allow more space for more water vapor to condense, and it becomes a self-propagating blister. When a panel is immersed in an environment, there is no cold wall effect because there is no thermal gradient. There are many coatings that can be put on a totally encapsulated panel, put in a beaker and immersion tested, and nothing will happen as there is no temperature gradient. But the moment there is a temperature gradient, it is a different story. That's why cold wall testing is so important. Generally speaking, a differential temperature greater than 20 degrees C between the top of the lining and the substrate is required in order for condensation to occur. If the temperatures are closer than that, condensation is unlikely and there is no cold wall effect. In service generally, there is a cold wall situation if there is a warm environment on the coating and it is cold at the substrate. Of course, if the situation is reversed and it's warmer on the outside than it is on the inside, then condensation won't occur at the substrate and the coating matrix will be tight. However, service conditions seldom occur where a coating is totally surrounded and at an even temperature. More often, there is a temperature gradient across the coating and substrate. Cold wall testing is used for a qualitative evaluation of the lining system after a predetermined exposure period. The test approximates actual service conditions, including the temperature differential between the internal and external surfaces of the equipment, which accelerates permeation of the lining by the media. The test generally conforms to ASTM 868, and the results obtained are used as a guide in conjunction with other criteria for the selection of a suitable coating for an application. Two similar tests are run dependent on the boiling point of the media. Where the service temperature of the media is below its boiling point, test method A is carried out, but where the service temperature is near to or exceeds the boiling point, test method B must be used. Method A apparatus consists of a cylindrical glass test cell into which is fitted a heating element, temperature probe and an aeration pipe. A reflux condenser is fitted to maintain the level and concentration of the test solution. Test panels are fitted either side of the cell and retained in place with tie rods. Method B apparatus consists of a steel cylinder flanged at either end. Welded to the cylinder body are bosses to take a heating element, pressure relief valve, pressure gauge and a thermometer pocket. The test panels comprise blanking flanges coated on the inner face and secured by either tie rods or bolts to the flange cylinder. The portion of the cylinder between the flange faces can be insulated to reduce heat loss. The test substrate is of the same material as the operational plant and suitable thickness to withstand the temperature and resultant pressure, plus a safety margin in the case of apparatus B. The panels are prepared on one side according to the surface preparation specification for the coating to be applied and marked for identification on the other. The blast profile is checked using a suitable profile gauge and the readings recorded. The coating is applied to the specification for the coating system and in a manner as closely simulating field application as possible, taking into account practical overcoating times, ambient temperature conditions, and delay between the finishing of surface preparation to the coating application. Where material is to be applied by brush or trowel, the material is likewise applied to the test panel. Where application is to be by spray, the test panel coating is also sprayed, with the panel in a vertical position. Wet film thickness of the coating is checked in an area of the panel not subjected to the media and outside of the gasket sealing area. Subsequent dry film readings are taken and both wet and dry readings are recorded. The dry coating thickness must be within 10% of the nominal DFT, or where a minimum is specified, the maximum reading shall be no more than 10% above the minimum. The coated panel is spark tested at the specified voltage and any defects found are repaired in accordance with the stated repair procedure for that material. The coating is carefully inspected visually before test exposure begins, and the colour, surface texture, gloss and any imperfections such as runs or sags recorded. The coating is allowed to cure for the period specified, taking into account field conditions, and where specified, elevated temperature post-curing is undertaken. Notes are taken of times and temperatures. The hardness is checked in an area that will not be exposed to the media, and this is also recorded. As far as is practically possible, the test solution is made identical to the anticipated service environment, with all conditions and concentrations of the environment recorded. The cell is filled from the top to approximately 3/4 full. Where aeration or agitation of the solution is required, normally where the solution is below boiling point, the aerator tube is fitted. The tube is fitted so that the outlet is almost at the bottom of the cell and connected to a suitable gas supply, usually compressed air, but where oxygen depleted environments are required, an inert gas such as nitrogen is used. The thermocouple wire is connected to the microprocessor control unit and the heating element switched on. The control is set to regulate the temperature at a level 10% higher than that normally attained in service, provided this does not occur a phase change of the solution. Where a phase change would occur at the higher temperature, the field service temperature is used. The cell is inspected on reaching temperature to ensure that there are no leaks occur, and the reflux condenser temperature is regulated to ensure that there is no loss of solution. The aerator is turned on and regulated to give the required amount of aeration or agitation. The panels are attached to the test cell with the coated side facing inwards, using gaskets suitable to resist the test solution and temperature. The cell is then filled approximately 3/4 full with the test solution and checked for leaks at the test pressure. The thermocouple wire is connected to a microprocessor control and the heating element switched on. Temperature and pressure rise are monitored during the heat-up period and the cell checked for leaks. On reaching the boiling point of the test solution, it will be noted there is a rapid pressure rise which continues for every degree of temperature increase. On attaining the test temperature, the cell reaches a state of equilibrium with constant pressure and temperature. Cells are monitored on a daily basis to ensure test conditions remain unchanged. Periodically, the cell is allowed to cool and dismantled and subject to an interim inspection. The apparatus is then reassembled and recharged with a fresh test solution. A visual inspection is made and the results recorded as follows. Colour. Report any change to the colour of the coating in the three areas of immersed, non-immersed and outside the test area. Surface gloss, report any change in gloss condition. Surface texture, note any signs of chemical or physical erosion. Blisters, measure the size and quantity of any blisters. Wash the test panel in fresh water and wipe dry, then check the coating for cracks or pinholing using the method originally used before the panel was put on test, and record the results. Using a magnifier to give 10 times magnification, carefully inspect for signs of surface cracking and record the location of defects found. Examine the test solution and note any changes that may have occurred. At the end of the designated test period, or upon failure of the coating system, the procedures described previously for interim evaluation are carried out, with the addition of the following. The hardness is evaluated in areas of the panel exposed to the liquid solution, vapor phase, liquid-vapor interface line, and outside the test area. A thermographic video camera is used to evaluate if there are any blisters not apparent to the naked eye. Gas-filled blisters show as white spots on temperature decline, whilst liquid-filled blisters show as black spots. Finally, a knife test is used to try and despond the coating from the substrate by pushing a thin, sharp blade under the coating. This is carried out by making entry first into the liquid exposed area, pushing on through the vapor exposed area, and finally into the area unexposed. The results at each area are recorded. Where the degree of chemical attack is questionable, a microscopic examination is carried out to determine the depth and degradation or permeation of the coating. There are various ways of preventing cold wall problems. Ensure good adhesion to the substrate with minimal micro voids. Use low permeation linings. Insulate to avoid temperature differential at the substrate. And finally, attenuate the lining thickness to reduce temperature gradient. Thank you for your interest and watching this video.